So, till where have you progressed?
Sorry?
Like where are you?
I implemented the whole thing in chapter 4 of the fast book myself, like the MNIST stuff and the pet classification stuff after that.
Okay.
But not afterwards. So
and the multicap. So you are on the pet classification. You have done.
Yes.
So, okay, but you have not got progressed to multi classification yet.
No.
So
have you done that?
have you
implemented all of it yourself?
No. So still 5 years. The pet classification, the softmax, and all negative log likelihood that I have done.
Okay.
But I haven't proceeded beyond
that. Chapter 5 is relatively small, isn't it?
Yeah, it is. I haven't been able to give anything in the last 2 weeks.
Okay.
I was, but I was not here and I was traveling, and yeah. Okay.
So
you want to share your notes on?
I mean, what I did was pretty, random stuff. Like I put codes. I'll still share it with you. I don't really have any notes.
You did the freeze unfreeze part as well?
No. I coded all of this until this point, and then you basically check the code that he shares, like using the pre-trained model. I don't understand why he uses pre-trained equals to false here, because isn't this a pre-trained model anyway?
Yeah, I think so. Pre-trained is, so he talks about something called as freeze unfreeze, right?
Yeah.
So pre-trained is equal to true or false, gives you that. If by default it's true, which means that it will learn with freeze. So everything until the last layer is freeze, and it will train one epoch on that, and then it will unfreeze. So basically, making it much more specific to our use cases. So the parameters
Okay, you
all
use
have
the
some
first. Okay, got it.
And if you do give false, it won't do that first part. It will unfreeze and do everything.
Okay, and he used a different. Also, I was trying to. So I'm basically trying to implement the same stuff as he does throughout the code from top. So you have, you already showed this in the last call.
Yeah.
So you have the tensors, you stack them up, then you experiment with the means. You have MAE, MSE, and you test with both MSE and MAE, and you get, the corresponding number. Right?
You're doing everything in a local?
Yeah, all of this is in local.
Okay. Even the GPU stuff?
No, I have a MacBook Air.
Okay.
And that too is like 3 years old, so it doesn't have anything. Yeah, just that, this model, this final model, it took 3 minutes on my system. And if you run it on a GPU, it would take like 10 seconds.
Yeah.
For one epoch, but it still gives the same accuracy. So I had some confusion around why this did not, basically come close to this line. Like it does match this one, but it doesn't really fit. But I think that's because the layers that we provide.
I think it did match. I think the first between the difference between the last and the first one is that the scales are different. That's minus 150 to 50, and the last one is 0 to 40.
What
and
are you talking about?
Looks
this one.
Yeah, the scale
no,
is
the
different.
Scales are different, but I'm talking about this thing, right? So after
I think
10,
it starts from 0 every time. It starts from 0 every time.
It starts from 0 every time.
So that's why like the initial part wasn't trained well. It starts from 0, like the random parameter. I think it's the number of epochs, right?
No, even if you make the epochs like 1,000, it would still have something like this, because always it starts from 0. So either we add something. Can you think of something? I mean, this is the model that we have at the moment, right?
No. See, what I think. Yeah.
Even what he created here.
Not sure. Right. I actually not thought of that. I was just looking at being equal more like the later part.
Right. Okay. So I kind of did understand part of it when I was doing it, because if it's not really, you know, long or a deep network, they are just 2 layers, right? And one of the layers is this thing here, where you have A, B, C parameters, and you have A into this thing, right? This is the function, and these are the parameters that we have. But with these parameters, you should be able to get, you know, this curve, this one here, the blue one.
Yeah.
Because if C is positive, and time becomes negative.
Okay, let's walk through that just a bit more. So what is it training against? Is it 0 the weight parameters? Is the number of epochs? What's the x-axis?
On the x-axis, you have time, right? So x values. So basically the input to our function.
Okay.
So this is a function, right?
Okay.
This is a function, right? And time is on the x-axis. So when time is 10, then you get the minimum of the curve. But here it's always, you know, when time equals to 0, you get the minimum. So basically C is always 0, because when time is 0, our model gives us 0, right? So C happens to be 0 all the time. Did you get a different curve for yourself? Because
it was something on the same lines.
Even what he did, okay, we do not have it here, but even what Jeremy did in the video, he managed to get something similar. And this value is like minus b by 2a or something, right? No, minus c by 4a.
So okay, I'm just let me figure it out. I have 40. Give me a sec.
Yeah.
So this is MNIST, right?
This is not MNIST. This is this random data that we generate. Yeah, this is the MNIST workbook.
Yeah. Okay. Just give me a second. I'm just trying to figure out what it was. Oh, this was, I think, when they were talking about SGD, right?
Yes. I mean, he's just explaining the concept here using some random data.
Okay, he started with some random data, right?
Yeah, he
some
starts
random
with
20,
this.
and he started with a. Okay, is the time versus speed? Okay, as
Yes.
time progresses along, what is the speed that gets?
What is the speed, right?
Now, and according to the function, is time minus 9.5. So it's 9.5. It gets around 0.
Right. I mean, at 9.5, it basically has the minimum speed.
Okay. And then he defines a function which will do it. Okay, so it is approximately. Now he gets a totally different graph, but yeah, it's the same. It starts with. I think it starts with 0. It doesn't get as good as yours actually. It starts with 0.
He kind of stops after a few epochs, I guess. But yeah, I mean, I was curious about why it did not move away from 0 here. I mean, there's no reason. We have a quadratic equation here. Our function is quadratic.
You're right, actually. I mean, there is a bias also. It's not just parameters.
And yeah, if this was not here, then we can understand that it would always, you know, have the minima at on the y-axis.
But yeah, agree.
Could be something with our loss function, maybe. I haven't really experimented enough with this. Maybe we can spend some more time at R and discuss.
I was just, I didn't give much time because this is a practice case for the SGD and stuff.
Okay.
Pretty much.
Okay, maybe I'll spend some more time, and if I find something, I'll share.
Good catch.
And then rest of it was pretty much the same as the workbook that he has. I just wanted to do it myself, so I tried coding it. And it's when you code yourself then that you realize some nitty-gritties that are there, like putting it in a tuple instead of just putting them like that. View function is pretty useful.
Yeah.
And we put them in data loader, combine them into data loaders. Also, there was one more thing that I was trying and I failed at. There was using my own optimizer that I defined here. It is the exact same thing that he does. Using this optimizer in this function here. So here, I mean, I couldn't use this optimizer here. It doesn't work. So you cannot put batch optim, basic optim, I guess. Basic optim. Here, it's going to throw an error. And it happens with the code that Jeremy has
sorry,
as well.
I lost you there. Can you repeat that part again?
So it's here they're using this SGD, right? The default inbuilt function, inbuilt optimizer. But you cannot use this optimizer here. So this is the optimizer that he defines in the video and in the workbook, in the notebook. But this optimizer cannot be used inside a learner as it is. You can use it here.
No, I think it can be used because I did exactly that.
Did you?
Yeah.
Okay, I wasn't able to do it. And
I think it's okay, I'll tell you why. The parameters that you passed.
Yeah.
So if you go ahead, so you pass the parameters directly, right?
I passed the parameters as part of the simple net.
Yeah, no, go ahead. So, okay, and this is how you created a basic parameter, right? Go down. So you created simple.net.parameters and you pass it, right? That is not how it should be done. You have to, so it's because parameters are actually, that's how it's declared. The model uses parameters which have to be globally declared, right?
Okay.
That's
no,
why you have to
when
break it down
you
to
declare simple net, right? When you define this thing, it actually, initializes the parameters within simple net.
Yes.
And if I run this thing, right, then it doesn't work because this one doesn't have a parameter attribute to it.
All right.
But if I use this thing, this one does work, or I can maybe run part of it.
Actually, like I did mine and it worked pretty fine. Like I was just like, I just.
You're using your own optimizer there.
My own optimizer I had written, and I had I just replaced the optimizer with STD, and it worked pretty well fine.
Okay, can you share that notebook?
Yep, I haven't started my. So give me a
no,
minute.
you just
time
maybe you can just attach it on Slack.
Okay.
Yeah. Okay. Yeah. So basically, just created this.
Now you have the optimizer is perfectly fine by itself. Whatever you created, that's how it should be created. The way you pass the parameters is the difference. Okay. Let me tell you. So what you have to do is, in the one thing where you pass the parameters, right? When you created the simple not that parameters, break it down to 2 lines. create in one and then pass in another.
Here?
Not here. No.
So this is where we define the simple net. I mean, this is another simple net. If you run this.
Yeah, simple net is fine.
So
then this, yeah.
So this one has parameters as one of the attributes.
Yeah, but you should do, I mean, it might be a different random. Yeah, no, it will get, yeah. Just pass in parameters.
Like this? Like you want me to pass it like this?
No. How can I show it?
I'll stop sharing.
I think my. No, you can continue sharing. I'll just. While my notebook is provisioned and given me some space.
Okay.
Okay, moving on. Yeah, let's move on.
Yeah. So that's it actually. I mean,
and you did the chapter 5. I think we had the questions we had completed, right?
Yeah. Okay, did we not complete these?
I think. Yeah, I think so. I think we had stopped around 23rd or 24th.
Why can't we use accuracy as a loss function? I remember discussing this one. Draw the sigmoid function. What is the special? What is special about this shape?
What's special about the shape? I believe like it's in like -1 or +1 for a long period, and there is a curve which.
Yeah.
So it distinguishes the other sides of zeros, like or like 0.5. There's a 0.5 sharp break there. Above that, everything is -1. Below that, everything is like a lot of +1.
Yeah.
The steep curve.
Yeah, it has is a steep curve around 0. Yeah. What's the difference between a loss function and a metric? Metric is what we try to improve. A loss function is the function that helps us improve the metric. But a metric does not definitely change at each point, whereas a loss function would have a different gradient at each point. So it keeps on improving the metric. Yeah. That makes sense.
Yep.
All right. And next, what's the function? New weights. This one's for you.
Yeah. Oh, sorry. Yeah, the function didn't tell. I think this is like lr.params.data. Sorry, params.data. We adjust it by the learning rate minus it equals to and learning rate into gradient.
Is there a name for this thing? I mean, this is the formula, right? You update.
Yeah, I mean you update the values.
Yeah.
I'm sure.
You're taking a step.
Yeah.
In the direction of the gradient, probably.
Yeah.
What does the data loader do? Data loader basically splits our data into batches, and then we can just define how we want to convert them into batches, whether we want to shuffle them or perform any other action. Right?
I think data loader. It splits into batches given the batch size, and then it loads them into GPU or the CPU in batches. It does that in batches.
This is okay. We've both done this independently. This one's for you.
Actually, past arguments. I think this is the list zip. So zip will convert it into
Yeah.
Yeah, it is a zip function. Zip will convert it into tuples of x and y each.
Yeah. What does the capital L do?
It's a list. So
It's
it's a
similar to
basically
a list.
Python list plus something. So the Fast.ai library provides a bit of different function, like added functionalities.
Okay. What does view do in PyTorch? It reshapes the tensor, right?
Yep.
It's same as reshaping, right? It doesn't do anything else.
Yeah, it reshapes. Yeah, it reshapes.
What are bias parameters in your network? Why do we need them?
What are bias parameters? What do we need them? Bias parameters. I think it's most likely an initial starting point, right? I mean, if we get to define it.
No, bias. All layers would have biases, right?
Yeah, like initial, for example, rather than starting at 0 or a random stuff, like if there is no input given kind of stuff, that's where the bias comes in handy, right? If all the inputs are 0, 0 or something.
If all the inputs are 0. No, even otherwise, if input is not 0, even then you're going to add some bias to it.
Yeah.
I mean, any linear model would have ax plus b x b x2 or something, and eventually there would be a bias term. Right? In our case, that was C.
That was C.
So every layer is going to have it, every linear layer. Why do we need them? Okay. If bias is not there, then when the inputs are 0, it's always going to be 0.
Yeah.
Yep. Bias prevents that. What else?
I think that's about it. It just gives you a value, like even if everything is 0, it just gives you something to look at.
Right.
Values, even if there is everything else. So if the parameters don't come into picture, like the parameter function, if those don't come into picture, then the bias is always there.
What does @ operator do in Python? Matrix multiplication?
Yeah, matrix multiplication.
What is the backward
What
method
does the method do? Backward propagation?
Yeah.
Right?
Right.
It's a feedback loop.
Yeah, and when you do backward, it's then that the gradients get calculated, right?
Yeah, right, exactly.
So for all the parameters in that function, the gradients get calculated if required grad is true.
So that happens in batches, right? So parameters get calculated once per batch, right? I mean, we have a batch size, right? The data loaders will put in each batch and it will calculate the gradients for each batch, right?
Yes. For each batch, the gradients are going to be calculated separately, but the overall parameters remain the same, right? So you initialize parameters, and then you run through the first batch, and then you optimize the gradient. Using the gradient, you optimize the parameters, and then the optimized parameters are fed into the next batch.
Yeah. Yes.
Right. So, yeah.
So the data loader will like calculate it per batch, the gradient.
Yes, data loader provides the batches, and then our function here,
model function,
basically, yeah, our model function does the backward propagation, and then we can
model calculation for all of the parameters that are in one batch. It will push them. It will calculate the model.
Yeah, it would calculate the gradient and then subtract them, and then the optimized the updated parameters are used for the next batch. So instead of doing it for the entire thing at once, we do it in batches, each time calculate the gradient and then optimizing it.
Yeah.
Why do we have to zero the gradients? This I'm not so sure. I mean, it calculates gradients on top of the existing gradient. I think it adds the gradients to the existing gradients unless we zero them, right?
Right. I think it takes like a multi-step rather than a single step. It's like, okay, I should take this plus I should take what is
the
value.
It adds the same two gradients. What information do we have to pass to learner?
What information? I think the model, an optimizer.
Right.
I mean, Fast.ai. I have read ahead that Fast.ai does, even if you don't pass it, an optimizer will take its own optimizer and stuff like that.
Okay.
But like, if we really want to control it, I think an optimizer, a model, a loss function, and a matrix.
Is it learner?
No, it was learner, right? Capital L.
Yeah.
Search for CNN learner. That's an LL. The question mark after it.
Oh, we're in a different notebook, that's why.
Okay. I will go for general interest.
By default, it uses Adam optimizer. Then you have to provide loss function, model, data loaders. Yeah, these three are mandatory. The rest of them it can take on its own.
Split rate will take it by default something. I think it's 80-20, I believe. The splitter function. Whatever data you pass it, it's a random 20. That's something in chapter 1 we had.
Show Python or pseudocode for the basic steps of a training loop.
Of a learner?
For a training loop. Yeah, for a learner.
For a training loop?
So a training loop would basically, yeah, good.
No,
so you have the data loaders. You take one batch from it, you initialize the parameters based on the dimensions of the data loader, and then you set require grads equals to true. And
I think we should first initialize the parameters, like not on every batch.
Yeah, you initialize it before taking a batch. And then you perform the operations corresponding to the layers, linear layer, then the model, and then you do a backward propagation, and then you calculate the gradients. I mean, gradients are already there, so you subtract them from the initialized parameters, multiplied with the learning rate, and then you zero the gradient. What else? And then you can calculate the metric that you want to calculate. Perform another iteration. This was one loop, one epoch, one loop, and then when you go through all the batches, that becomes one epoch, and you keep on doing the same stuff. And also, after the end of the epoch, you would basically take the average of the accuracies of all the batches, because the metric that you're getting is only for one batch, and you want to display for one epoch. So you take the average of all the accuracies or the metrics. Yeah. All right. You're next.
Okay. What's ReLU? A rectified linear unit. That's what the short form is for. Draw a plot of it from values from -2 to +2. Yeah. So just pass in nn.ReLU.
Right. Yeah. And I also did not understand there was this discussion, a question that Rachel asks during the video.
So -2 to 0, it will be So it will be from.
It's going to be 0 before 0, and it's going to be a x equal to y line afterwards.
Sorry, there was a connection.
Okay.
There's a hello.
Yeah, I can hear you.
You there? Okay.
Yep.
Yeah, sorry, you were saying something. Yeah.
I was saying I did not understand the part where Rachel asked that can the gradients be 0 for all of them, and because of which, so if all the layers result in negative values, then ReLU is going to give 0 for all of them. As a result, the parameters don't get optimized any further.
Yeah.
So I did not really get that part.
Yeah. So the point was if you see from -2 to 0, it's a horizontal line, right?
Right.
Right, and then it from 0 to 2 it slopes forward. So for a horizontal line, there is no slope. Right? You can't. So the slope is 0. Which means the gradient is a gradient is basically the slope, right?
Mm-hmm.
So if everything is negative value, if you take a ReLU, it will always output a horizontal line for that range, right? Which means that the gradient will be 0.
Gradient would be 0, and it doesn't get optimized further. But
Yeah,
for the next batch,
I
mean, this is for one particular batch, right? For the next batch,
yeah.
this cannot happen, right? And the parameters would change.
Yeah, I mean, what she was saying was a hypothetical scenario. If, for example, for every batches with then for a couple of epochs, then every epoch we take a different batch, right? A batch of different elements, right? So somehow, if like we get some data which will have, or our function, it's at the end of that, it's a function, right? A function and a combination of a model, it always outputs a negative value, then a ReLU will totally destroy it.
Yeah, so it has to be negative for all the values.
Yes. Every time, every time
All
it
the
will be
batches and all
executable,
the
then it's a
values.
problem.
Yeah, then it becomes yeah. But Jeremy said this does happen, but I mean, right now it doesn't feel like it can happen. We cannot have a negative value for all the values.
And it's all of softmax. It's all sigmoid function, right? So if the values are really low, then sigmoid will convert it to like in the low zeros.
We are using ReLU, no? We are not using softmax.
Right?
So we are using a linear function, and then we are putting
Yeah.
in the end.
I got confused. Yeah, right. You're right.
But when you are adding nonlinearity, instead of ReLU, if you use softmax, and then maybe some point down the line you have ReLU, then it's more or less the same thing.
Hold on. So okay, we have in us neural networks, we have, so ReLU is something in between two layers, right?
In between
it's
two
a
layers,
in between layer, but the previous and the second one are matrix multiplication layers, right?
Right.
And I think we do a sigmoid with that.
It really depends. I mean,
so model, okay.
Here, see, here
so
we
sigmoid
use ReLU.
softmax,
Here we
that's
use
the model,
ReLU, right? Yeah, that's the model. So we
that's the model.
we could use sigmoid here, and then I mean again we use another nn dot ReLU here, right? So we can
right now we use sigmoid. I think also during the function loss function, right? We use sigmoid primarily in the loss function. So converting the predicted outputs to a range between 0 and 1 or here, right? That's when we use sigmoid for, right? It's in the loss function. MNIST loss is the ReLU, right? Sigmoid, right?
Yeah. Right. MNIST loss function we defined somewhere. So that basically is the sigmoid function.
Yeah.
Yeah.
So that's where we use the Sigmoid function.
You're using it to convert it into 0, minus 1 and 0, basically 0 and 1.
Yeah, 0.
Eventually. But when calculating the gradient, you're not really using that thing.
But we use gradient after we use the whatever the prediction from the loss function, right?
Yeah.
I think that's what we
All right. Okay. I'm still a bit confused about why it's a problem to have ReLU and use leaky ReLU instead to avoid the zeros. I feel like it cannot happen that for all the data you get 0 negative
right.
values.
Definitely not for all the data, but yeah, for some of the data, like even if it's multiple batches, we can have negatives.
Yeah. Okay.
And I think it's more about keeping it in mind so that we tweak our model rather than like
yeah, just
it
like
will always
something that can happen or
yep, right.
in the worst case scenario.
Yep.
What is an activation function? Activation function is a non-linear function that we apply to a linear function when you're building a neural network, so that it can basically take the form of any function that you're trying to predict.
Right. Yeah.
If you do not put an activation function, then the neural network is nothing but a big linear function.
Yeah, combination of neural networks,
yeah,
one after the other.
Yeah. What is the difference between you? This is for you.
Yeah, so F is basically Fast.ai and NN is your PyTorch version. And I think the difference is that one is a class, and I think f.relu is a class, whereas nn.relu is f.relu is a function, whereas nn.relu is a class that we can extend.
Yeah, right. Okay, I haven't used f.relu, but it's something like the loss functions that they used earlier. Right. Yep. This one is used when defining the model. This one is used to maybe.
Now, like we can use nn.relu and then we can instantiate using brackets, and then we can call it with again a second pair of brackets.
Okay. If I provide 0.8, does that work? No.
There's a different function.
Must be tensor, not float. Would this work? All right. It does work.
Yeah, minus 1 does work. And then nn.relu, you have to initialize it just with a bracket, and then we have to call it with a function.
Right. Okay. Got it. The universal approximation theorem shows that any function can be approximated as closely as needed using just one nonlinearity. So why do we normally use more?
I think there's a difference in theory and practical.
No, and I think you would need a lot of parameters if you were to do it using just one layer.
Yeah.
And that would basically mean, massive matrix
slow.
multiplications. Yeah, computationally really challenging. And instead, if you combine a lot of linear and nonlinear layers, you could do this with much fewer parameters and less computation.
Yep.
All right, cool. We are finally done with chapter 4. I mean,
yeah.
I'm finally done with chapter 4. Good breeze. Should we set up some time in the middle of the week, or do you want to discuss this next week?
Yeah, we can.
Are you working full time?
I am working full time. Yeah. But I think I am free. So morning time at 9:30, 10 o'clock was fine for me. Because my work day starts around 12 o'clock and goes like deep into the night.
I'll try to go through this one, chapter 5 today. Or maybe tomorrow by end of the day I should be able to finish it, and then I'll ping you on Slack and then we can set up some time to discuss it.
Yep, that's it.
Yeah, cool.
Yep. Cool.
Thanks, Sham.